So let's talk about number 13 and 14 because they're kind of the same thing. So on number 13, here's your basic setup. When something is floating, okay, this is the most vital thing on number 13. When something is floating, you only have two forces involved. You have the gravitational force pulling down, and you have the buoyant force acting up. That's it. There's nothing else. There's no strings. You're not pushing it down. You're not lifting it up. Nothing. Okay, that's it. That's it. Boom.
Mr. Buoyant,
What?
can you rotate the camera?
Oh, you're so demanding.
Thank you.
Yes. How's that?
That's good.
Okay. All right. So, you only have two forces involved. Now, the only way it's going to float is if these two are equal. So, all you have to do on 13A is just write the buoyancy force is going to equal the gravitational force acting on the aluminum. That's all you have to do on 13A. Okay, that's it. There's nothing else to it. That's all. Now, on B, I want to write, oh, how can you calculate the weight of the aluminum using density? So on 13B, all you have to do is go, okay, well, that's just going to be the density of the aluminum times the volume of the aluminum times G. Now, this is what's important. This is the entire volume of the aluminum. Okay, this isn't the part that's submerged because we're talking, I'm just saying, okay, hey, I'm going to give Party Girl a block of aluminum, and I want her to figure out how much it weighs. But she knows the density. So she can find the volume of that aluminum, multiply it by the density, multiply it by G, that's the weight of the aluminum. Okay? That's all you have to write. That's it. There's nothing else. Now, when you get to D, on part D, you want to write an expression of the buoyant force. So here's the deal. Your buoyant force, because that's the way that the liquid, and the liquid is mercury, so that's going to be the density of mercury. Now, here's what's going to be important. This is going to be the volume that's below the surface. It isn't the entire volume of the aluminum. It's only the part that's below the surface. So we're going to call that volume submerged times G. Now, we don't know what it is. I don't care what it is because it's going to work out to be a ratio anyway. So then, on to get E, here's going to be the setup. You're going to take the density of that aluminum, or excuse me, the density of the mercury, times the volume that's submerged, times G, is going to equal the density of the aluminum, times the volume of the aluminum, times G. So, your G is going to cancel out. Here's the density of mercury. Here's the density of aluminum. Now, you're asked to express this as a percentage, okay? So, the only way this works is there's an equal sign in here, which is important. So, you know that the volume that's submerged is less than the total volume of the aluminum. So, you can take the volume that's submerged, divide that by the volume of the aluminum. But you're going, but Mr. Burkamp, we don't know these numbers. You're right, I don't care about those numbers. Then, over here, you're going to take the density of aluminum, which you can find on your sheet, divide that by the density of mercury. These two numbers you know. So if you can take the density of the aluminum divided by the density of the mercury, that's going to equal the volume that's submerged divided by the total volume, because you're just asking for a percentage anyway. So if you take the density of the aluminum divided by the density of mercury, and let's say you get 40%, 0.4. What that means is that 40% of that substance is going to be submerged below the surface. Okay? That's all you have to do. Now, on 14, you're going to be lifting this piece of metal out of the water. So, this tension going up is going to be the difference between the gravitational force acting down and the buoyant force acting up. There's a couple problems like this on your assignment as well out of the book. Okay, they're standard buoyancy problems. So here's the deal. FG is going to be easy. because I gave you the mass of the steel plate, that's 18,000 kilograms, multiply that by G, there's the downward pull of gravity. Okay, you've got that number. The tricky part is the buoyant force. Okay, so your buoyant force is going to be the density of the water times the volume of the steel times G. But here's the problem. You don't know the volume of the steel, but you know the mass of the steel. So you can go, oh, the density of the steel is going to equal the mass of the steel divided by the volume of the steel. So you can go to your sheet, find the density of the steel. I gave you the mass of the steel, that's 18,000 kilograms. You can find the volume of the steel. Once you get that, then you can put that in here. You know the density of the water or the salt water. Then that's your buoyant force. You've got the gravitational force acting down. So all of your answers on 14, B, C, and E should start with a 1 and should be something times 10 to the 5th. Okay? All start with a 1 and something times 10 to the 5th. Okay. On number 12, not all of them, but a lot of your answers on number 12 should start with a 4. If none of your answers on number 12, if none of those start with a 4, you have completely screwed it up. Okay?
Mr. Burkamp,
What?
I have a sort of general question kind of relating to this. So I'm just trying to understand, when something is like floating on the water, like if it's a cube or something, then the amount of water that is, like the weight of the water that is displaced is equal to the total weight of the cube, right?
No. If it's floating, yes, the buoyant force will equal the weight of the cube. That's true.
But then if it sinks, then that doesn't apply anymore.
No.
Okay, cool, thanks.
No, because the reason it sinks is because of, if you've got a body of water and you put a rock in there and it sinks because the downward force acting on the rock is bigger than the buoyant force acting upward.
Okay.
Okay?
Okay, thank you.
No problem. Now, speaking of the problems out of the book, okay? So, if you look on number 23 out of the book. So here's this barge, okay? And if you ever become a barge captain, you have to know what happens when you transition from salt water into fresh water. Because salt water is more dense, so you're more buoyant in salt water than you are in fresh water, okay? So it's particularly true, like if you're going underneath a bridge, if you're barely making it underneath the bridge in fresh water, once you transition into salt water, like if you're out in the ocean, that boat is going to rise up. So you have to take that into account, because if you're in salt water, that thing's going to sit higher in the water. So here's the trick on number 23, is that you're given the dimensions so you can find the volume of the salt water that you displace. So you can take length times width times height. So you can figure the volume of the salt water that this barge is going to displace, because you know how far it sits in the water. Then you can also, once you get that, you can multiply that by the density of the salt water, and then you can get the mass of the salt water that it displaces. Now, here's the trick on number 23. The mass of the salt water that you displace has to equal the mass of the fresh water that you're going to displace, okay? But you got to displace more fresh water in terms of volume to get that same mass, because the density of fresh water is less. So the trick on 23 is that you find the mass of the water that you displace, okay, which is going to be around 50,000 kilograms, okay? Then you need to find the volume of fresh water that needs to equal that mass. So the trick on number 23 is that you're going to take to find that volume of the fresh water that you have to displace. Take the mass of the water that you have to displace and divide that by the density of the fresh water. Okay? So this is about 50,000 kilograms. It's a little bit less than that. Okay, so when you do the math, that's what you get. So then when you get the volume of that fresh water, okay, then set that equal to length times width times height. And you know the length and width of the barge, then solve for the height. And but this H is how much is below the water. That's one of the things you have to watch for. This is what's below the water. So, here's your steps on 23. Find the volume of the salt water, find the mass of the salt water, set that equal to the mass of the fresh water that you displace, find the volume of the fresh water that you have to have, divide that by the length and width, and there's your height. Okay? So what you should see is that your answer on 23 is above 0.8. Okay? Because it's asking on that one, like, how much of that is below the level. 24 is kind of a similar type thing, but let me give you a hint on 24. So remember that volume is also equal to your cross-sectional area times your height, okay? Keep that, because any volume is like length times width times height, which is also area times height, okay? So that's going to be a key. So on 24, so your buoyant force is going to equal to your gravitational force, and that's going to be mg, right? So that's the density of the fluid times the volume of the fluid times g is going to equal the density of the wood times the volume of the wood. Now, here's the trick, okay? You're asked to find a height. Well, your g's are going to, you don't have to worry about that g because that's going to be on both sides of this, so you don't have to worry about that. Just cancel that out. So this is going to be the density of the fluid times the area times h is going to equal the density of the wood times the volume of the wood. But if you remember, because it's a cubed, and this is why this looks horrible, but it's actually not, that's the density of the wood times like a length cubed, okay? Because of the fact that it's all the same size. So this is going to be, what you're trying to solve for is h. So you know the density of the wood, you know the density of the water, your cross-sectional area, because it's a cube, is 0.1. So this is going to be like 0.1 squared. This is going to be 0.1 cubed. So you need to solve for h. So this is going to be 0.1 cubed. That's going to be 0.1 squared. You know this. Excuse me, this is going to be 0.1 squared. Solve for h. Now, the tricky part on 24, it asks for like how much of the block is sitting above the water, not how much is submerged. So that's what you have to watch for on your answers on 24. Okay? All right. Anything else you want me to go over on that assignment?
Can you go over 25?
Out of the book?
Yes.
Yeah. So 25 is just like kind of the ones on my assignment. So what page is that on? 428?
Yeah, it's 428.
You said 25, Lauren?
Yeah, I said 25.
Yeah, so on 25, here's the deal, right? So on 25, you're asked to find the tension in the string, right? So find the weight of that aluminum block. You're given the volume, and they gave you the density. So you can figure out the mass of the block, multiply that by g, there's your downward force. You're in ethyl alcohol, okay? And if you look in the book, they give you the density of ethyl alcohol, right? So then you can find your buoyant force. So the difference between those two is the tension that's on the string. There you go. So your answer to 24, excuse me, your answer to 25 should be around 2. And your answer to 26 should be around 0.1. 26 is the same thing, it's just you're keeping it from floating up. So on 26, your buoyant force is bigger than your downward force. Okay?
I have have a question about something I did on 23.
Okay?
I worked it like differently than you, but I still got the right answer. I ended up, so I found the buoyant force of like the water when it was in the seawater or whatever, and then I put that into, I don't know how to explain this.
Diego, as long as it made sense to you, that's good.
But like, I'm just wondering if buoyant force is that, like, is there an option to go through there to find it, or did I do something wrong?
No, you could go through the buoyant force.
Okay, that's just what I was making sure.
Yeah.
I don't want to make sure I do something weird and just by chance.
Yeah, because the buoyant force still has to balance out the weight of the ship, no matter what.
Okay. Okay, cool, thank you.
Okay, good. Going once, going twice. Got it?
Wait. Can you go over number 22, please?
Number what?
22.
You sort of trying to find the density of the alcohol?
Yeah. Well,
Okay.
Yeah.
So you've got the diameter. It's neutrally buoyant. Okay. So you just have to find the density of it. So on that one, you just take mass divided by volume. It's neutrally buoyant just means that it will exactly float in. It has the same density as the fluid. That's all that means. So you've got the mass, change that into kilograms. Now, because it's a sphere, that volume is 4/3 pi r cubed. So this is just a conversion problem. Take your mass, change that into kilograms. Take your volume and use the radius. Don't use the diameter because they gave you the diameter. You have to use the radius. And then just take mass divided by that volume, figure out that density, then look on your chart and figure out what fluid it is. It should be one of the alcohols, by the way.
Okay, I just made it really difficult for no reason, so.
Okay, Joel. Yeah. Oh, yeah, literally, just find the density. Take mass and divide it by volume. That's all you have to do. Okay, anything else? Once, twice sold? Okay. All right, so that's done. Now, for those of you that are zooming in, now I'm starting to go over the lab. So I didn't staple this because you're going to have to staple like the graph at the back of it. Okay, so on this lab, there's 3 distinct parts to this lab. So the first part of the lab, you're going to take yonder pressure sensor, and what you want to do is set, now, and I tell you, if you look on this second page, which I can move right back to the lab, there it is. So you've got over here, you're going to look at the relationship between pressure and volume. So you can think of this as like a second grade class. So what's going to happen is that you're going to set the volume to 5 milliliters. So you're going to set the syringe where that leading edge is at 5 milliliters. Now, this is going to be important. You're going to set it at 5, and then you're going to screw it on to the gas pressure sensor, which is hooked up to the lab quest, which is showing you pressure, and then you're also going to use the thermometer, so you're going to have pressure and temperature. So, hook it up, and you're going to record this reading, which is like 97.4 kilopascals. So, that's the default setting for pressure. So, eventually, you're going to have to draw graphs where you put this in pascals. Remember, pascals are the same thing as Newton meters. So, 1 atmosphere of pressure, which is kind of what the baseline is, that's 101.3 kilopascals, which is 101,300 newtons per square meter. So 1 kilopascal is 1,000 pascals. So if you have to do that conversion, just multiply by 1,000. It's not a big deal. In terms of this graph, all we're trying to get an idea of what's going to happen. So I've got this hooked up. I'm at 97.4 kilopascals. So then what you're going to do is you're going to leave this thing hooked up, and then you're going to increase that volume to 7. So you're going to pull back, and now you're at 7. So visualize this. I'm in my 2nd grade class, okay, and the little ankle biters are running into me. Imagine now I'm going to keep the same number of ankle biters. They're going to stay at the same temperature. No Skittles are allowed in. But now I'm going to make the room bigger. So what's going to happen to the pressure on my ankles created by the ankle biters? It's going to decrease. I'm going to have fewer collisions. So then when I go to 7, okay, then that pressure drops to like 72. So hold it there, let it stabilize out, okay? Then you're going to go to like 9. So you're just going to make the room bigger and bigger and bigger. But you're going to keep the number of kids in the room the same, and you're going to keep the energy of the kids the same. Okay? Got that? That's the first part. Now, the second part on page 3, this is going to be the number of puffs. Okay? So, puffs are going to be like the number of kids. Okay? So the first thing you're going to do is you're going to set this at 3 milliliters. So you're not connected to the sensor. You're going to set this thing at 3. So we're going to have like 3 kids in the room. Okay? Got it like this. I got 3 kids in the room. Now, I'm going to pull back and I'm going to make the room at 10. Okay? So I'm going to pull that syringe back so I put 3 kids in here, but now I'm going to adjust the size of the room to 10. And I'm going to record the pressure. Okay? So, after that gets done, I'm going to disconnect the syringe. Then I'm going to put 6 kids in the room. So now I'm going to have 2 puffs. I'm going to screw this back on. Now, when you tighten this, this isn't like the strongman competition. Don't ask me for a wrench to spin this thing. Just get it snug. That's all you have to do. So I put 6 kids in the room. Then I'm going to pull the syringe back till it reaches 10. Got that. Let it go. Go to 9. Now eventually you're going to go all the way up to like 6 puffs, which is going to be 18 kids. So then you're going to go to 18. Put that on there. But then you've got to compress it down. Whoop. Then you've got to compress it down. Then you've got to shrink the room to 10. So on that second set, sometimes you're going to increase the volume to 10. On the other ones, you're going to decrease that volume to 10. But make sure that you disconnect that syringe in between each one. So we're keeping the size of the room the same. We're keeping the energy of the kids the same. But we're putting more and more kids in the room. Okay? So if you go with that analogy there. Now the third part is what's going to take the most time. So on my Thursday group, when you all get here, you'll hear the same speech. But here's what you want to do with you guys. The first thing you guys get over there, you're going to take a 600 milliliter beaker, fill it up to about the 500 milliliter mark, and put it on a hot plate and get that starting to warm up, because it takes a long time for this thing to heat up. So you can do the first 2 experiments while this thing is heating up, because if you wait to heat this up, you're going to run out of time. So you're going to heat this up, you're going to put this on and start to heat it up. Now, this is going to use a different one. So you've got to make sure that this test tube, and by the way, don't break these, don't roll them on the floor. My first block managed to break 2 of these today. Seriously. It's like they were doing gravity experiments. Oh, if I drop the test tube, how long does it take to hit the ground? So if you've seen like the last Indiana Jones movie with Sean Connery, where they're going after like the Ark, not the Ark of the Covenant, but the what are they going after, that one with Sean Connery? It'll come to me. It was like the last chalice that was used as the Last Supper. So anyway, so they tell you don't break the seal. So whatever you do when you start this last experiment, don't break the seal. So with that one, don't use the syringe because we want the volume to remain constant. So you can take this hose, hook it up to here. So this is going to be on here like this, and you're going to have this in here. Now, you're also going to have a temperature probe hooked up. Make sure the temperature probe is not resting on the bottom of the beaker, because then you're measuring the temperature of the bottom of the beaker. I want to measure the temperature of the water. So you want to have a setup like this where you can keep that temperature probe in the water. So you're going to heat the water up to maybe 60, 70 degrees. So you got to monitor that temperature. I don't want that water to boil. You want to heat it up to about 60 or 70. Once it hits 60 or 70 degrees, turn off the hot plate, let that temperature stabilize for a little bit, and then you're going to record the temperature and you're going to record the pressure. Then you're going to add ice to it to begin to cool this down. So you're going to add some ice until the temperature drops maybe like 10 degrees, okay? Then you're going to let it stabilize, record that new pressure. Add some more ice. Now, what you'll see is that because you're adding ice, the water level is going to rise. So I'm going to give you a cute little 50 milliliter beaker, and you're going to use that to dip the water out so that it doesn't overflow. So you're just going to keep adding ice until it drops maybe 10, 15 degrees. Record that pressure, add some more ice, and keep going down like that. But that's the first thing that you need to do. I'm also going to give you all a sheet of graph paper because there's 3 graphs that you all have to draw. So here's what's going to happen tomorrow. I'm going to send out a video on this last lecture on fluids and the Bernoulli principle and things like that. I'm going to send out the answer key to that last assignment, okay? Because you all have enough grades and stuff, and at this point, it's not going to make any difference anyway in your grade. But the onus is going to be on you, okay? So that's going to happen. So we'll send that out tomorrow. So my Thursday group, if you're watching this, you all are going to do the lab on Thursday. On Friday, we're going to do this review. On Tuesday, y'all are going to take the test. You guys are going to be here. Next week, you're going to be here anyway. But my Monday group, you all are going to be expected to come into the school and take the test, okay? Then Wednesday review. On Thursday is your final. You guys are going to be expected to come back and take the final, okay? So on next week, you can have a test Tuesday. You can have a test on Thursday. Okay, let's go do